Right. I hope other people who aren't here are also watching them. I doubt that they're partying. Well, I'll share the video with you so that we'll see if they're really partying or not. Where is this? If of course I can get my Firefox to. Do you guys know this one? The Simpsons. So how do I fit this here? That works? Wow. Full screen? Okay, there you go. Somebody has a good suggestion. And I do play. I guess I can hook up.
Hey, listen, Homer, something weird happened back in high school. Teenage Carl and I were walking down the hallway when...
You two, I want you to take this box and bury it in the woods. The true results of this election must never be known.
Tell you what, we'll do it under one condition. Our parents want us to go to college, but with a bad enough recommendation from you, we can stay here and party.
Okay, screw this up, and it's Carnegie Mellon University for the both of us.
So I like this one because it attests how honest our students are. But playing hard is important also. So this shouldn't discourage you from partying, hopefully. You can still take off your spring break and submit your assignments late. That's why we have the 5 late days. Okay. Let's go into a more exciting topic, which is hopefully caches. So I'll skip these things quickly. Hopefully you're attending the lab sessions to discuss your baseline simulator. So in the last lecture, we reviewed the basics of memory, DRAM, SRAM, and bank organization. So hopefully you remember that. We'll go into that later on today. Talked about memory hierarchy and the locality principle, temporal and spatial locality. That's the reason why memory hierarchy is around. We talked about caches, their basic operation, and set associativity. So you should know by heart how a cache operates by now. And you're going to explore this in your lab assignment. Hopefully, you'll come up with new replacement policies also. And we stopped at write handling. Today, we'll wrap up the basics of caches and go into main memory. This is an exciting topic. Not a lot of architecture courses actually cover main memory in detail, but this is a topic that's close to my heart. I do a lot of research in main memory, and I think it's a very important part of the system. So hopefully, it should be interesting. So we talked about this. What's in a tag store? In a cache, you have a valid bit, you have a tag, and you have replacement policy bits. And we talked about what kind of replacement policy bits you can have depending on the replacement policy you implement, right? True LRU is difficult to implement. And we talked about whether you want to have a dirty bit or not. If you have a dirty bit, well, if you have a write-back cache, then you need to have a dirty bit, right? The question is, when you store to a cache location, do you also store to the next level, or do you also store to memory? If you don't want to store to memory while you're storing to the cache, then you should mark that cache block with a bit saying that this cache block is dirty so that you don't lose that update, right? At some point, you will need to update memory because that's the real value that you're going to store to the cache. But this is not the only option you have. You could have a write-through cache. This is called a write-back cache, basically. You don't write back to the next level. You don't write to the next level when you do the store, right? You write to the next level sometime later. Write through cache, when you do a store to a cache block, you also do the store to the next level, if you will, to all of the levels. Then all of them are write through caches. So what are the trade-offs associated with it? We talked about this. Write back, the downside is now you need to manage this dirty locations in cache, right? You need to have a bit in the tag store indicating the block is modified, and when that's about to get evicted, now you send the block and write it back to the next level. Okay? The good thing about this is, if you have multiple writes to the same block, all of those writes happen while the block is in the cache. Which means that you don't need to do multiple writes to the next level. Which means that you save bandwidth to the next level, right? especially if you're writing to a block many times while it's resident in the cache, those writes do not get exposed to the higher levels in the cache. So this saves bandwidth between cache levels, and which means that it also saves energy, right? You don't exercise that bus between the two caches. Write-through, on the other hand, is simpler. You don't need to manage these dirty blocks, if you will. We will talk about cache consistency later on, but if you have multiple processors with multiple caches, what might happen is they can access the same location, right? They can cache the same location in their caches, and let's say one of them writes to that location. Ideally, you would like the other processor not to read the old value, right? You would like the other processor to read the new value that's being written to this cache over here. Now, if you have a write-back cache, there's a problem, right? You need to somehow ensure that the processors have the same value for that block. But if you have a write-back cache, this processor is keeping the new value in its own cache. So how do you ensure the two processors see the same value for the same cache block or same location in the cache? Now, we'll get back to this later on when we cover multiple processors on a chip or across different chips. But write-through caches simplify ensuring that different processors see the same value for the same cache block. This is called cache consistency, or more commonly cache coherence problem. And hardware, normally in existing systems, ensures that each processor reads the most up-to-date copy of a cache block, if you will, or a memory location. And ensuring that it's simpler if you have a write-through cache, because when you write, you don't just keep that up-to-date copy in your cache, but it goes through all the levels, right? Does that make sense? We'll get back to this. Okay, so that's one advantage of write-through caches. The disadvantage is, of course, it's more bandwidth intensive, right? You have no coalescing of writes. Whenever you do a write, you write it back to the next level. Okay, there's another issue related to writes. When you do a store to a cache, do you actually allocate that cache block? Let's say you're trying to do a store, you got a cache miss. Normally, the way we describe it, when you're trying to do a read, you actually bring the block all the way from memory into the cache and store it, right? But with a write, do you want to do that also? This is a design choice again. Allocate on write miss, that's one policy. Answers this question positively. Yes, you allocate a block. No allocate on write miss, answers this question negatively. Basically, you don't bring the entire cache block and store it in the cache. Yes?
Isn't just having write-through not sufficient? Because if I read something from memory, and so now it's in my cache, and then someone does a write-through, right, in another cache, then I still have the old value in my cache.
So it's not sufficient, yes, but it helps cache coherence. So you're going back to that topic, right? Yeah, it helps. We'll get back to that. It's write-through itself is not sufficient to ensure cache consistency. You need to have a mechanism. But write-through helps it because you need to check only the all of the writes get propagated. So you have a processor, you have L1 cache, and let's say you have L2 cache, and then you have another processor, and then you have L1 cache, and then L2 cache. Here you write to a block, but if this is not up to date, then you need to check this cache also, right? But if they're all up to date, then you just need to check this cache, assuming these are inclusive. But we'll get back to that. Okay? But good thinking. That's okay. So let's get back to whether you actually allocate on a write miss or not. Allocate an entire block. This actually, let me step back a little bit. This design choice exists even on a block that you just do a read on, right? Let's say you're doing a load. You still have the design choice of whether or not you bring the entire block from main memory and put that into your cache. So if you somehow have a mechanism that predicts whether or not you're going to access that block later on, you could decide, if that mechanism says, oh, I'm not going to access that block ever again, you could decide not to place that into your cache. Right? So in a sense, this design choice exists, but it's a little bit more interesting with the writes. Yes?
But if you're like putting your trust in like locality, why would you not want to bring it to your cache?
So yes, if you know, for example, that a block is going to be touched only once and not going to be touched again, then you don't want to bring it into your cache.
That's rarer than it being touched multiple times.
It depends on the application, right? But we can talk about that later on. Okay, allocate on a write miss says when you write to a location, you bring the entire block. The good part of this is you allocate the entire cache block, and you can now consolidate writes instead of writing each of them individually to the next level, assuming that you have locality. Again, this assumes that you have locality, right, in the writes. Again, this is simpler because write misses can be treated the same way as read misses, assuming you're bringing, whenever you have a read miss, you're bringing the cache block into the cache, and that's the assumption so far. The downside is it requires a transfer of the whole cache block. So if you're just doing a write once, or if you're doing a write to the entire block, you really didn't need to transfer the entire block, right? Does that make sense? So let's say you have a 64-byte block, and your process, this is part of an array, and let's say you have, I guess, 4-byte words, which means you have 16 words here. The processor is doing a streaming write, if you will. This is streaming write means you're writing to consecutive memory locations new values. Let's say you're doing this. CI equals AI plus BI. You computed AI plus BI, you're writing it to CI. And C0 happens to be here, 1 through 15 happens to be here. Basically, you will write to the entire cache block, right? Which means that you really didn't need to bring in what the old value was in memory. Well, you don't know this, of course. So that's why you waste bandwidth by bringing in the entire value from memory. So no allocate, but we'll find a solution to this. That's why I put a question mark here. It doesn't really require the transfer. Yes?
If you're doing write back, then it makes sense, right? Because then you move it to the cache and then just write it right there.
If you're doing
write back, then this makes sense, right? To move it to the cache. All right, yes. Move the entire thing.
not necessarily. These are orthogonal decisions, right? Well, write back assumes that you have the cache block in there, but yes, write back in a sense assumes that you allocate on a write, but you can still do this for some blocks potentially. So no allocate means basically you don't allocate. This conserves cache space if locality of writes is low, right? Okay, so sectored caches address this problem that I just talked about. The idea here is you divide the cache block into sub-blocks, if you will, or sectors. A sub-block is also called a sector, and associate a separate valid and dirty bit associated with the sub-block. The idea is when you're doing a write, you don't allocate the cache line, for example. What you can do is, let's say your sub-block is the granularity, the same granularity of your write granularity. Let's say it's a word. You can just allocate the sub-block, right? You can just make this valid and dirty, and everything else becomes invalid and dirty, and you can set the tag. This way you don't need to transfer the entire cache line into the cache. And if you're doing a streaming write, what will happen is you'll write to this sub-block first, this sub-block next, this sub-block next, this sub-block next, and everything will become valid at some point. And you wouldn't have brought the entire cache line from memory. So that's the idea of sub-blocking. Basically, you don't need to transfer the entire cache block into the cache. And now you have more freedom in transferring sub-blocks into the cache. So you could use this design for improving read performance as well, right? What do I mean? Perhaps now you can design, make a design choice saying when you get a miss to half of the line, you bring some of the sub-blocks, or you bring one sub-block, right? So it gives you more flexibility. The downside is it's more complex, right? Instead of having one valid and one dirty bit for the entire block, you have, I guess in this case, 16 valid and 16 dirty bits, assuming your sub-block is of the granularity of a word. And if you're doing this for reads, let's say you're reading a few sub-blocks instead of the entire cache block, then it may not exploit spatial locality, right, when you use this for reads. Okay? So sector caches have been used, and they're still employed to especially help the write performance in existing applications, in existing processors. Okay, instruction versus data. We had briefly, somebody asked this question earlier, and I told that we were going to get back to it. Well, I guess I have everything here. You have options, right, with instructions versus data. Do you have separate caches, or do you use the same one unified cache? If you use a unified cache, essentially this is the same as dynamic versus static partitioning of your cache space, right? You have some cache space. Do you have instructions and data interspersed in different cache blocks? Or do you have an instruction cache versus data cache? Of course, let's say this is n. This is n divided by 2, perhaps, or n divided by 2. You could partition the space in different ways also, right? The advantage of this is it's dynamically partitioned, right? If your instruction working set happens to be small, you'll use only that much. Whereas here, if your instruction working set happens to be small, you'll underutilize this cache, right? And if your data working set happens to be large, you'll really need a bigger cache. Whereas if you had them dynamically partitioned, a single structure, then you could perhaps get almost perfect hit rate. Whereas right now, because you're statically partitioning it, you'll get misses in this case. Whereas you have enough space to store both. Well, the downside is because you're dynamically partitioning, now your instructions and data contend for cache blocks here. Actually, there's an even more important downside. Instructions and data are accessed in different places in the pipeline, right? And you really would like to be able to access instructions and data at the same time, right? And if you look at a pipeline, what happens is this is the fetch stage, right? That's where you really need the instruction cache. And this is the memory stage. That's where you really need the data cache. Which means that this structure needs to handle both accesses in parallel if you want your pipeline to flow, right? So this is the real reason. And also, they need to be accessed at different places. This is the real reason why instructions and data are divided into separate caches. Because you need to enable multiple accesses in parallel, and these accesses need to be done in different parts of the pipeline. And if you look at the layout of the pipeline, if you put a unified cache here, then you somehow need to route the wires to both of those places, from both of those places. But if you split the caches, then it's a lot easier to access instructions from here and data from here. Make sense? Okay. Yeah. So first level caches, because of this reason, and because remember that first level caches are tightly integrated with the pipeline design, because of this reason, they're almost always split. But the second level caches, so you have an L1I cache and L1D cache, but the L2 cache, it's not dictated. its design requirements are not dictated by the pipeline design. It doesn't need to provide data directly to the fetch stage or directly to the memory stage. And it doesn't need to provide data in one cycle. That's why L2 caches are usually unified between instruction and data. And you have control logic here. Okay? Okay. So, again, multi-level caching in a pipeline design, first level caches. If you look at them, well, I think I covered this earlier before, but I wanted to have a slide also. Design decisions are very much affected by cycle time. And if you unify them, again, your latency increases as well. That's because design decisions of these two caches are affected by cycle time, they're usually smaller and lower associativity. Remember, associativity increases latency. Right? And because you want to get the data as fast as possible, they operate the way I described. You access the tag store and the data store in parallel, right? So that but that's not the only way to access a cache. In fact, if you look at the second level caches, what happens is tag store and data store are usually accessed serially in a second level cache. Meaning you still have an associative cache, but you have a tag store and data store. What you can do is access the tag store first and get the hit miss signal. And you have, let's say, let's say this is 16 way. You get a hit miss signal and a signal specifying which way hit, assuming it's a hit. Now, once you know this information, you can access the data store with the same address, but you can access only that way that you know hit, right? So you have 16 of these. You don't need to access all 16 of them. Now you know which way actually hit. You access only the one that hit. If it's way 0, you enable only this way in the data store. And if you actually missed, you don't need to access the data store at all, right? Because you already figured out that the data is not there. So this is called serial tag data access. And what's the benefit of it? Well, the benefit is it saves a lot of energy, right? If you have a huge cache, you don't need to access the data store, all of the ways in the data store in parallel, only to select data from one way if you hit. And you don't need to access the data store at all if you miss, which means you save a lot of energy because of eliminating this access. What is the downside? There's always a downside. Now your latency to access increased, right? Because you're not doing this in parallel. You don't get the data almost at the same time. Well, as you determine whether you hit or miss. Now you incur the tag store latency, full tag store latency, plus the data store latency. But it could be okay for the second level cache or third level cache, right? Because it's not as critical. Latency is not as critical at that point, right? Remember the equation that we had, the recursive equation? We didn't have power in that equation, but most modern processors do this to save power because they have very large caches, right? In fact, I think I may be wrong, but IBM Z series, the latest IBM Z series processor has a 48 megabyte L3 or L4 cache. So imagine enabling all of that 48 megabytes. And I think that's a 32-way associative or maybe 64-way associative cache. It's in that order. You can correct me if I'm wrong. Maybe we can find those numbers and tell the exact numbers for the next lecture. Okay, so this attests to the fact that higher level caches have different design requirements because they're not tightly integrated into the pipeline. So the decisions you make here need to balance the hit rate and access latency and power that I didn't put here. So usually these are large and highly associative to maximize hit rate. Latency is not as important as the first level. That's why you do design decisions that optimize for power. Okay. And also, you make them big because latency is not as important. That's the other reason. There's also another thing that I want to discuss, which is the serial versus parallel access of the levels. If latency is actually very important to you, you may want to access multiple levels in parallel, right? Or you may want to start accessing the second level before you know the result of the first level, right? That's called parallel access. Most processors use serial access. Second level cache is accessed only if first level misses. And third level cache is accessed only if the third level misses. But if latency is really important to you, you may want to while you're accessing the first level, or maybe while you're accessing the second level, you may want to send a speculative request to memory, let's say, to start the memory access. Right? That saves some latency if you miss. If you hit, well, that increases your bandwidth requirements. That's the downside. And if you hit, you may want to cancel that request, right? Because you already have it in your cache. And that increases complexity, canceling that request. Okay, I'll skip this. But this basically says second level cache does not see the same accesses as the first. In a sense, the first level acts as a filter, right? You see very different access stream in the second level. And you could actually exploit this fact potentially. But let's not go into that. You can think about that. Okay. Any questions so far? Let's talk about cache performance a little bit. Cache performance is affected by many different things that we've discussed. The size of the cache, obviously. The block size, associativity, the replacement policy, and the insertion placement policy that I briefly alluded to. Do you actually cache a block or do you not cache a block? So let's take a look at some of this. Cache size, this is usually the curve you would see. As you increase the cache size, the hit rate initially increases, and then it tapers off. Why? Because your entire working set starts fitting into the cache. This is common for most programs. So basically, bigger caches can exploit temporal locality better, but not always better. If locality is not present in your program, then you cannot exploit it with caches at all, right? If all you do in a program is go through an array and never revisit that array, then you don't have much temporal locality. Right? You can have spatial locality that can be exploited, but not temporal locality. So your hit rate cannot always be 100%. Right? Well, you knew that your hit rate cannot be 100% because the first time you touch something, it's not in your cache, right? That's called a compulsory miss, as we will see soon. Okay, so too large a cache. Here I plot the hit rate, but this is different from performance, as you know. If you plot performance, actually, this could be a curve like this, right? Potentially. Not exactly. Because you have hit and miss latency, right? If you have too large of a cache, now you're increasing your hit latency. And you're also increasing your miss latency. And you may degrade your critical path as well. Too small a cache, you don't exploit temporal locality well, and useful data is replaced often. So, okay, working set, I think I defined it last time, but you guys know about the notion of the working set, right? That's the data plus instructions. I guess you touch an application references while it's executing. And this is defined based on a time interval, of course. You could think of the entire application from the time 0, beginning of execution, to the end. It touches an amount of data, and you could aggregate how many bytes you touch, and that's the working set of the entire application during its execution. If you have a cache large enough to hold that, and if the application actually has locality, then you can get the best possible hit rate you can get by sizing the cache that way. But okay, block size. Block size is the size of the data that's associated with an address tag, right? This, in this case, 64 bytes. What happens as you increase or reduce the size of a block? assuming you keep the size of the cache constant. You have a given cache size, 1 megabyte. Do you choose to have 8-byte blocks or 256-byte blocks? Well, there's a trade-off, right? I'll get back to that. If you have 2 small blocks, you're not exploiting spatial locality well, right? And have larger tag overhead as well in terms of design. Because remember, a tag is associated with a block. As you make the size of the block smaller, your tag size increases. If you have 2 large blocks, well, you have too few total number of blocks in your cache. Right? In a sense, if you have a 1 megabyte cache and your block size is 1 megabyte, only thing you have is a single block, right? If you happen to touch some other megabyte in your cache, in your memory access stream, then too bad, you miss. Whereas if you have a smaller block, maybe you could have cached that other piece of the megabyte that you've touched, right? So likely there are 2 problems with it. Your hit rate reduces because you have too few number of blocks. You also transfer likely useless data if your spatial locality is not good. And basically you consume extra bandwidth and energy and your performance reduces. And this is a common graph averaged across many applications. As your block size increases, your hit rate increases to a point, and after some time your hit rate starts decreasing because you have too few blocks in your cache. Okay. This is pretty straightforward, right? Okay. Block size, one thing I want to mention is block size is not necessarily the unit of size of the unit of transfer between different cache levels, if you will. So let's say you have a data cache with a 64-byte block size. You don't necessarily need to have a 64-byte bus to transfer the entire block, even if you're transferring the entire block whenever you bring a block. To save cost, to save pins, well, or to save wires in this case, you might want to have a 256-bit bus here to transfer half of the block, right? Which means that you transfer half of the block in one cycle, the next half in the next cycle, right? Make sense? So this saves you cost. And this is especially important when you're going off chip, right? This is on chip. When you're going off chip, you cannot afford to have 64 times 8 pins dedicated to just data. That's 512 pins. Those are expensive, right? So what usually happens here is you have, actually a lot of processors have a 64-bit interface, data interface. You transfer 64 bits at a time, which means that it takes, I guess, 8 transfers across the bus to transfer the entire block from DRAM, or you could have an L4 cache that's off chip, right, onto your chip. Okay? And sub-blocking also helps this, right? Sub-blocking, whenever you transfer a piece of the block, you just make that valid quickly. Right? So the processor can actually keep accessing the cache while the cache is filling other parts of the same block. Okay. Okay, large cache blocks. Well, this is the notion of critical word. Whenever you get an access, obviously you're not accessing the entire 64 bytes, right? The processor is doing a load. It's logging into register X. And it's doing a, let's say, 4-byte load. At that point, you really need that 4-byte. Right? This is called the critical word. The critical word is the word or data that the processor actually needs at that point. So most processors are designed to supply this critical word first, all the way into the cache hierarchy. Now, what does this entail? Well, critical word can be anywhere in the cache block, right? Which means that when you access the cache, when you get a cache miss, what needs to happen is that critical word needs to be specified with the requests for the cache block. So downstream you say, this cache says, I want the cache block at this address, but please give me this word first, right? Because that's what the processor is really waiting for. So that's the upside of the critical word. Well, there's a downside to it. Now it introduces complexity, right? Critical word could be anywhere in the cache block. And you need to ensure that you get the critical word from DRAM first, and then you get the other words, if you will. And if the critical word is in the middle, it's not, your request is not simply for the cache block anymore. Your request is, give me this word first. Okay. So we've already talked about sectoring, but one way of reducing the downside of large cache blocks while getting some of the benefit of them is sectoring, sub-blocking. Basically, you can transfer only the sub-blocks when you get a cache miss, and not the entire block. The advantage of this is basically, well, the advantage of this is now you're amortizing the tag storage overhead still across the blocks, right? The disadvantage is you're not exploiting spatial locality across the entire block, at least while you're filling the cache. Right? After you've filled all of the sub-blocks, you can exploit the spatial locality. Okay? So this gets some of the benefits of a full large block because you can amortize the tag storage overhead, but it still has some of the downsides because you will underutilize your cache if you don't have good spatial locality. Okay. Okay, associativity, I think we've already covered this, but as you increase the associativity, again, your hit rate increases and then tapers off. And it tapers off very quickly, actually. We've talked about this, so I'm not going to go into this. Usually from 1 to 2 ways, you get a big jump in hit rate. This doesn't mean that, but in some cases, you really need associativity. So what happens is in your cache, there are some sets that happen to be hot, if you will. For some reason, data maps to these sets, and you get a big miss rate just because of that set. So what you would like to do is really have large associativity for this set and perhaps small associativity for other sets. Now that's hard to do. But there have been many solutions proposed to reduce this problem. This is the problem of hot sets, if you will. Too many data items, too many blocks that map to this set, that map to a hot set, are accessed at the same time. And there are many solutions proposed for this, and we will probably get back to this in a later lecture. So before I end this associative discussion, do you need to have does your associativity need to be a power of 2? I'll ask this to you right now before I ask it on the exam. Yes or no? Who says yes? Who says no? Okay, a lot of people say no. Nobody wants to venture a guess for yes? Or defend that? Okay. Why is the answer no? Who wants to? Go ahead.
You can design logic to only use a certain number of, like, certain number of associativity, but like it would be best to have power of 2 because then you would utilize your index bits best.
Okay. So associativity has nothing to do with the index. What you said is totally right, except until the index part. So associativity, the only thing that associativity determines is how many blocks are mapped to the same set, right? Mapped to the same index. So you get your index. Associativity says, how many ways do you have? Let's look at well, if you have a direct map cache, your associativity is a power of 2. But if you could have a 3-way cache, right? you still can index this array nicely because the size of each way is 2 to the index bits, if you will. And you get the tag out, and all you need to do is compare, right? The tag. And this tells you which way matches, if you will. And based on that, you control the mux. And you have 3 items coming from the data store, right? These are the data ways. Data way 0, data way 1, data way 2. Well, that's it. That's a 3-way associative cache for you, right? Okay? In fact, people have implemented 3-way associative caches. Okay. Let's classify some of these cache misses. We kind of implicitly did this. There are some cache misses that you can never eliminate with caching. These are called compulsory misses, right? First reference to a block always results in a miss, right? Because you haven't cached it. That's the definition of a first reference. So caching cannot eliminate compulsory misses. You have to do something else. What is that something else? You can predict that you're going to touch that block, and you can bring that block into the cache before you touch that block. That's the idea of prefetching. And we will cover some of that. Okay. So if you're, in a sense, if your locality is poor, which means that you're going through this array, compulsory misses can dominate your cache miss rate. Right. There's another kind of miss. This is the capacity miss. You can reduce these by increasing the size of your cache, normally. These happen because your cache is too small to hold everything that's needed. And the way we define this is as the number of misses that would occur in a fully associative cache with a perfect replacement policy that are not that is of the same capacity. Okay? And conflict misses are the kind of misses that I kind of described here. They happen because you conflict in the set. Basically, if you really want to be a purist, you have to define it as a conflict miss is any miss that's not compulsory and that's not due to capacity issues. So, and there are different ways of eliminating these misses. Compulsory misses, well, too bad. You cannot eliminate it by designing a better cache. Do something else. That's the answer here. Do prefetching. Conflict misses, you can eliminate them by having more associativity, right? Or you can reduce them, well, not eliminate them, reduce them by using other ways to get more associativity without making the cache associative, because there are downsides to making the cache fully associative, right? And we can, we'll briefly touch on this. I'll get back to these later on when we have a cache lecture, cache optimization lecture, if you will. But you can think of how hashing could help. Remember, when we indexed into the cache, we picked some bits from the address. And the reason conflict misses happen is because a bunch of blocks map to the same index, and they happen to map to the same index at the same time. You happen to need those blocks at the same time. What if you randomize this index somehow? Instead of using these bits, you have a predictable randomizing function, hash function, randomizing hash function, that disperses, if you will, these index bits to different locations in the cache. That way you can better utilize your array. Right? And people have proposed solutions like this, some of which are employed. And we can get back to this. Capacity misses, well, there are different ways of eliminating these. You can increase the cache size. But you can also utilize your cache space better, right? Try to keep the blocks that are going to be referenced. Right? Or not insert into the cache blocks that are not going to be referenced. And potentially software can help here, right? The software can potentially, if the programmer knows that the block that's brought by this load instruction is not going to be touched again, there could be a hint bit associated with the load instruction saying that don't bring this block into the cache. And you could do that in x86 processors. There are non-temporal bits associated with prefetch instructions, if you will. It's called non-temporal. So you can mark an instruction, a load, as non-temporal. And this gives a hint to the hardware saying that, oh, this load, the data that's brought by this load doesn't have good temporal locality. And it's the hardware designer's choice to look at this bit, design logic that looks at this bit and doesn't cache the data. Of course, the hardware designer, again, can ignore this, right? Because it's just a hint provided to the hardware. It doesn't affect correctness. Okay? And in many processors, some of these bits are actually ignored. The software designer can say the load is non-temporal, but because of design choices that the hardware designer makes, because this does increase complexity, right? The hardware designer can choose to not implement the behavior specified by this. And in fact, this is written in the x86 manuals also. I'll show you some of those later on when we talk about prefetching. Okay, and you can do even more management in software that would get you much better hit rate, right? So for example, you can divide your working set such that each phase fits in the cache. When you're doing a matrix multiply, you can do the multiplication in the parts of the matrix that are in the cache at that point. Right? And we'll get back to that also. Okay. So how do you improve cache performance? Well, these are all ways to reduce miss rate, right? But miss rate is not the whole story. Reducing miss rate actually can reduce performance, as we discussed before, if you evict blocks that are costly to refetch, or if you increase hit latency, or if you increase miss latency, right? So there are other ways to improve cache performance. You could reduce miss latency, or you could reduce hit latency. Remember, this is the average memory access time. Hit rate times hit latency plus miss rate times miss latency. You could improve average memory access time by reducing any of these components. Now, reducing hit latency is usually very hard, unless you reduce the cache size. Right? So usually, when you're designing a cache, you try to optimize the miss rate and miss latency. These are some of the things we will talk about sometime later. Some of the things we have already talked about also. Actually, multi-level caches reduce miss latency, right? Reduce the miss latency of this level, if you will. Critical word first reduces the miss latency of the critical word. Sub-blocking, again, reduces the miss latency because you don't transfer the entire thing. I'll talk about two other things right now, non-blocking caches and multiple access in parallel, because I think these are important, and these are all employed in existing processors. Any questions so far before I continue, though? Okay. Do you know all of this stuff before? Hopefully not. Good. Okay. So non-blocking caches, the idea here is when you have a cache miss, can you continue operating in the processor? Right? Can you continue generating more cache misses? Why would you want to do that? Well, you've seen out-of-order execution, right? You get to a load gets a cache miss. Can the cache handle more misses at the same time? That's the idea of non-blocking caches. Can later accesses be handled while a previous miss is outstanding? This is also called lockup-free caches. This was described first in the seminal paper in 1981 by David Croft. The idea is very simple. Yes?
Would this be for superscalar then? If they're single pipelines, they can still be stopping in a single cache. You can't go past that operation waiting on data.
No, even if it's a scalar processor, if you have out-of-order execution, you may execute a load later on, right? For superscalar, there's a different problem that we will see also. Yeah. The idea is basically add extra logic. Add extra control logic that keeps track of the status and data of the misses that are being handled. And this logic is called miss status handling registers, or miss buffers, if you will. When you get a cache access, that access checks these miss buffers, MSHRs, to see if a miss to the same block is already pending. If it's pending, a new request is not generated, and the pending request is added to this structure, if you will, such that when the data comes back, the data is supplied to that load. That's the idea. And if actually there's a pending request and the needed data is available because you've transferred part of the cache block, then that data can be supplied directly to the load. So this requires the buffering of outstanding miss requests. Okay. I guess I'll go back to this later on. But this is also called a miss buffer. Basically, you keep track of outstanding cache misses and the pending load store accesses that refer to the missing cache block. How can you implement this? I'm not going to spend too much time on this, but basically, you need to have a structure that in a single entry keeps track of the cache block address, some control and status bits, like which subblocks have arrived, whether you actually issued this request to memory yet, and data for each subblock. And for each pending load and store, some information. So if you look at this, it's something like this. This is the entry for a miss buffer. Well, the entry could be valid or not. This is the address of the cache block that is missed, that you're waiting on. Is this issued to memory? And then for each load or store that's waiting on this cache block, well, is it valid? What's the type? What is the offset of the block that it's waiting for? And what's the destination register? Right. So that when the data, when the block, subblock, if you will, comes back from memory, that load can be woken up. Right. Does that make sense? Simple, right? So what happens on a cache miss? Basically, you search the MSHR for a pending access to the same block. If you find it, then you allocate one of these load store entries. If you don't find it, then you allocate a new MSHR, miss status handling register entry, if you will. And if there's no free entry, at that point the processor stalls, right? If you get a load, it misses in the cache, and there's no free miss buffer entries, the processor then needs to stall. If you didn't have this structure, then the processor needed to stall at the end of the first miss, right? Because you cannot handle any other misses. So when a subblock returns from the next level in memory, the structure checks which loads are actually waiting for that subblock by looking at this block offset, and forwards the data to the load store unit, and deallocates this one of these load store entries in the MSHR, and writes the subblock into the cache or into the MSHR. And there's a design choice there. Do you write it into the cache right away? I'll let you think about that. And if this is the last subblock, then you can now deallocate this miss buffer. Okay. So there are design choices. When do you access these MSHRs? Do you access them in parallel with the cache or after cache access is complete? Well, these are tracking misses, right? Cache misses. So there's no reason to access them in parallel with the cache. If you access them in parallel with the cache, now you're putting something that's really not supposed to be, oh, this is the wrong one. That's really not supposed to be on the critical path, on your potential critical path. Because you size this cache, this D cache, to supply data very quickly. If you have this MSHR structure, if you will, miss buffer, what you need to do is access them in parallel and mux out the data, because MSHR can hit or the cache can hit. Right? Now you're adding one more mux into your critical path, if you will, potential critical path. So it's not a good idea to put the MSHRs here, although it may potentially improve performance, right? Because the data may not be in the cache, but maybe in the miss buffer, because that subblock just happens to be there. Right? So MSHRs do not need to be on the critical path of the hit requests. If you put them here, then you're putting the MSHR into the critical path of the hit request. And that's a very bad design choice. Because, well, which one is the common case? Cache hit, or, well, you already answered, right? Cache hit or cache miss MSHR hit. Right? Cache hit is by far the most common case, because data doesn't stay in the MSHR for too long. Right? Once you complete the access of the entire data, you write it into the data cache and eliminate it. So if you look at MSHRs, Pentium 4, for example, has 8 of these. it can have 8, one core in Pentium 4 can have 8 outstanding cache misses. It has a 126 entry instruction window, which means 126 instructions can be present in the machine at a given time. And the data cache can be waiting for 8 cache blocks from the lower levels. Okay. So let's get back to this MLP, the notion of MLP. Just wanted to give you the term. Basically, MLP is the notion of generating and servicing multiple memory accesses in parallel. And parallel means you could start the access every cycle, or you could start the access in the same multiple accesses in the same cycle. Okay. These are still parallel concurrent accesses, if you will. So why do you want to do this? We've already kind of covered this with out-of-order execution, but let's say you have an this is an isolated miss, if you will. This miss to block A, there's no other miss that's happening at the same time, whereas these are parallel misses. You miss, the processor misses on block B, and also generates a miss to block C, let's say because of out-of-order execution. Now what you have done with parallel misses is this enables latency tolerance. It really overlaps the latency of different misses. Right? So while you're not stalling for only one miss, you're stalling for, in parallel, 2 misses. Which means that these misses are now less costly in terms of performance. So if you had the choice, if you will, of servicing 2 misses in parallel versus serial, you probably would like to service them in parallel, right? So let's say you need to do 2 accesses to cache block A and cache block B. One option is, let's say this is your time, you access cache block A first, and then cache block B next. Because let's say you're doing in-order processing. Well, now the full latency of both cache blocks are exposed, right? Whereas if you did this, you access cache block A, and you generated the miss to cache block B at the same time, or almost the same time, then your service latency for both misses gets halved, if you will. Right? That's the notion of memory level parallelism. And this is one of the major benefits of out-of-order execution. You really overlap the latency of long latency cache misses so that you don't stall for one of them. Okay? There are other ways to achieve this memory level parallelism, this kind of tolerance, which is like multi-threading, prefetching, or something called run-ahead that I had done for my thesis, PhD thesis, which we may get back to later on. But that's the idea of memory level parallelism, and that's why having misstatus handling registers helps in a single core. Okay. What time is it? So let's take a break for 5 minutes, and then we can come back to high bandwidth caches. So it looks like Lamanya did the research very quickly and found out the size of the L3 cache in IBM's latest Z series processor, Z196. If you look at it, it's 24 megabytes on chip. That's a relatively large cache. I think Intel has 12 megabytes. Is that true? Yeah. And there's also, and this is implemented in some technology we didn't discuss. It's an embedded DRAM technology that's denser than SRAM. A lot denser than SRAM, but not as dense as DRAM. But it's implementable on chip. And there's also a 192 megabyte L4 that's shared by 1, 2, 3, 4, 5, 6 chips, if you will. So, okay. Before we finish caching, let's talk about at least the basics of caching. Let's talk about how to handle multiple parallel accesses at the same time. We kind of covered this with Cray, right? Cray 1's memory system, remember, it was banked into 16 banks. And we will cover this several times, actually. Hopefully we'll hammer home the concept of interleaving today. But why do you want high bandwidth caches? Why do you want high bandwidth memories in general? Let's look at the specific example of caches. Well, we want multiple instructions per cycle, right? Superscalar, VLIW. If you want to execute multiple instructions per cycle, you want to supply multiple pieces of data per cycle as well to those instructions that need them. So how do you ensure the cache can handle multiple access in the same clock cycle? And there have been several solutions proposed for this, and these are by no means specific to caches. These are concepts that are applicable to any kind of memory. So let's cover some of these. True multiporting, virtual multiporting, multiple cache copies, and banking. True multiporting, the idea is, remember the SRAM cell I showed you earlier? You had 6 transistors. With true multiporting, now you add multiple read or write ports to the cell itself, so that you can do multiple accesses in parallel to the cell. You can do 2 reads from the 2 different ports, right, to the same cell. Well, of course, obviously, you can see from this picture, this comes at a cost, right? It comes at a cost because now you have multiple word lines that go to the cell, multiple bit lines to be able to read from different cells, or even the same cell at the same time, which means that this comes at the cost of latency. You have more capacitive loading in these buses, and your latency to the access for the single cell increases. More power, more area. Right. Well, there's also one more thing that you need to deal with if you have this. What if you have a read and write to the same location at the same time? Right. The logic I showed you here doesn't handle that, right? So you have to handle it with peripheral logic. And you need, basically, this is one example that I pulled off on the web, if you will. You have dual port memory cells. You can think of each port as a left port and the right port. And you need to ensure that one port is not reading the data while the other port is writing the data, right? So how do you do that? Well, you need to have something that they call here the Semaphore Cells, which basically checks whether one port is doing a write to the same location that the other port is doing a read or write to. Right? And it basically grants, basically you have an arbiter to a row, if you will, based on this. And you can look at these figures. They're relatively easy to understand. So true multiporting has some disadvantage, as we've seen. So people have looked at things like virtual multiporting. The idea is actually quite clever. The idea is to timeshare a multiple port, timeshare a single port. Let's say you want to do 2 accesses per cycle. Why don't you do the first access in the first half of the cycle and the second access in the next half? This way you don't need to deal with this peripheral logic, for example, as long as you get the ordering right. But the ordering is specified by the instruction ordering anyway. And you can still get 2 ports. Well, 2 accesses per cycle, right? Well, the downside is each access needs to be significantly shorter than this clock cycle, right? Which means that you need to design your cache such that it can supply data at a higher frequency than your processor. But this was actually used in Alpha 21264, which was a very fast processor, fastest processor of its time in terms of frequency. Its cache was even faster. And they had to do, it was a 4-byte machine, 4 instructions per cycle, and the cache could supply 2 loads or 2 loads per cycle. And that's how they did it. One load went in the first half of the cycle, the second load went in the second half. Of course, the question is this scalable? Scalable meaning, can you actually do this for 16 loads? Now, it becomes difficult, right? You have to divide your single cycle into 16 little subcycles, if you will, where at the end of each subcycle, you get a result. And that's difficult. Your cache needs to be very high frequency, if you will, or high bandwidth. So other solutions, one other solution is to have multiple cache copies. This way you don't duplicate. You don't have true multiports, which means that your cell can be fast. So the big disadvantage of the true multiporting scheme that I showed you is your cell itself is slow, right? And if you scale it to, let's say, 8 ports, now you have 8-bit lines, 8-word lines, accessing the same cross-coupled inverter, which means that the loading on that inverter is very high, which means that it's very slow. Right? So people have proposed other things like having multiple copies of the cache, entire tag and data store. Right? This way you could think of one port accessing the first copy and the other port accessing the second copy, and you could do these access in parallel at the same time. Right? And this was used in Alpha 21.164, the previous generation Alpha. Well, there are several issues with this. One is, what do you do with the stores, right? Now you have a consistency problem, if you will, across the different copies of the cell. You don't want to do a store to only one location, so you need to have the stores update all of the locations, which means that you cannot parallelize the stores. Again, scalability is a problem, which means that if you want to have 8 ports, what do? 8 copies of the cache? You probably don't want to duplicate 8 copies. You probably don't want to have 8 copies of your 128 kilobyte L1 cache, for example. Your cache becomes 1 megabyte now. And you're really wasting that space, right? It's really the same data that's being stored here. So a compromise is what's called banking, interleaving, that we've seen with Cray. Right? The idea here is you divide the memory locations that you store into multiple banks, if you will. Instead of having a single monolithic structure, you have 2 smaller structures that you can access in parallel. Here, bank 0, bank 1. And one option could be to have even addresses go here and odd addresses go here. Let's say block addresses, which means that cache block 0 in memory goes to bank 0, cache block 1 in memory goes to bank 1. Remember the cache blocks in memory? You can think of memory as divided into cache blocks logically. Oh, there it is. And if you bank your cache, this is the view of your memory, main memory. You really have cache block 0, cache block 1, cache block 2, cache block 3, cache block 4, ... And this is your cache. And when you get an address, you have byte and block that determines which byte in the block you're accessing. And you have a bit called bank. Which bank is the block in? And that determines whether you go to bank 0 or bank 1. And if you choose that bit to be the bit that's right after the byte and block bits, then you're essentially interleaving even cache block addresses and odd cache block addresses across the banks. Right? Even ones go to bank 0, odd ones go to bank 1. Make sense? So that's what's happening here. Of course, that's not, we will get back to this, but that's not the only choice you can make, right? You could choose this bit to come from anywhere in your address, right? And there may be different reasons you may want to do that. We'll get back to this. So which bits to use for bank address is important. And the key here is address space is partitioned into separate banks. We're not having copies, right? We didn't copy the entire thing. We just divided the entire thing. So what are the upsides? There's no increase in the data store area, right? Here we copied, so we doubled the area. Here we didn't double the area. And we can still have parallel accesses, assuming those accesses go to different banks in the same cycle. Right? What Cray did was, Cray did not have two ports. What they had was 2 banks sharing a single port. Right? They could initiate accesses every cycle and service them in parallel in different banks, and they could get one access every cycle. But they couldn't do multiple accesses at the same cycle. So this is a more costly design, if you will. You could access different banks in parallel because you have different buses. You could access, you have one bus for this bank and one bus for the other bank. So as long as your accesses go to different banks, it's great. You can access them in parallel. The downside is you cannot always satisfy multiple accesses to the same bank. Right? Well, you cannot satisfy, this should be, you cannot satisfy multiple access to the same bank in the same cycle. Right? They're serialized. If you want to be able to satisfy them, you divide the bank into, well, you have more banks. Right? Well, what is the downside of having more banks? Let's interconnect, right? There needs to be some logic that determines which bank the access goes to and which bank the data comes from. Right? So let's say your load is coming here. This is your load instruction. This is another load instruction that's coming here. The address of the load may be located here, right? And the address of this load may be located here. Which means that you really need a crossbar to route the address of this load to the bank it needs to access and route the data back to the load. Yes?
If you have two loads that run to the same bank, how do you determine which one gets loaded in which cycle?
Okay, so you need to have control logic that schedules those loads, basically. Which means that you need to buffer those loads, and you need to have a controller that does that. So this adds complexity to the design, definitely. It's not like having multiple cache copies, or it's not like having true multiports. But it's significantly less costly. It comes at the cost of complexity, but you can still preserve the latency, if you will, of the access of the cell. And you can scale it reasonably as long as you can build this interconnect well somehow. Okay, so bank conflict, I've already defined it. Two accesses are to the same bank. How can these be reduced? I'll let you think about this. Again, you could use similar methods like hashing, right? Instead of using a single bit from your address, maybe you try to randomize it. Right? Or maybe you somehow have the software map your data nicely such that you try to access, you access different banks at the same time. We will see the same question. We'll return to this question in main memory very quickly, actually. And there's a question in your homework that you need to deal with. Okay, which alternative is better? Depends on how you define better. And if you're interested in this, you can take a look at this paper. Although there are shortcomings, like with every paper, there are shortcomings with this paper too. Because it's hard to answer this question. You need to do simulation, but also you need to figure out what are the access latencies for these different alternatives, right? So how do you figure out those access latencies? Well, you have to design all of these different options and place the different options in a high-level simulator, and that's what these authors did. Okay, any questions? So now you know of different ways of enabling multiple concurrent accesses. You already knew it, kind of, but we'll go into more detail also. Okay, main memory. We'll get back to caches later on. So what we've covered is really caches here, and caches here. What happens if you miss in all of these caches? You need to go to main memory. Right? So let's take a look at how main memory is organized. I'd like to think of actually any kind of memory chip or the memory system like this. You have an address that's given to it, and you enable the memory system. If you're doing it right, you enable the memory system, and the memory system gives you back some data. And essentially, if your address is n bits, you have 2 to the n memory locations, each of which contain k bits, and you get the k bit data. This is the abstraction, right? But memory system is not designed this way. Underlying, you have basically a bunch of different structures, levels, that kind of resemble each other. In fact, you could take this and divide these numbers n and k somehow, and have little replicas of this inside internally. And internal to each replica, divide that number by some other number and have replicas inside also. And that's how you design a scalable, hierarchical memory system. And we will see how that's organized soon. Yes?
What is the chip enable?
So chip enable, we will see the use of it soon, but you can enable or disable the memory system. It's essentially enable. Do you actually have an access to this chip? Should it supply the data? We will see this soon. So remember, this is a memory bank organization. I've already told you how this operates. Normally, you have a 2D storage array organized as rows and columns. And usually, a row has many columns than you really need. So you get a little piece of a part of this entire row when you access it, but to reduce the cost of the overall array and to optimize the latency of the overall array, you actually read much more data than you need. Okay? So you supply the row address and the column address. And we've already seen this. SRAM, DRAM, they have similar structure. And we'll get back to some of this. Let's cover some fundamental concepts. We've already talked about address space. That's the maximum size of your main memory. Right? This is the total number of uniquely identifiable locations in main memory. And this is different from your ISA's address space. And we will see why. Right? Your ISA, we defined this for the ISA. Right now we're talking about real implementation. Your address space, physical address space, can be much smaller than what your ISA specifies. Right? Your ISA can specify 64-bit address space. That doesn't mean that you have 64 bits to the 64 locations in your memory. That's a large memory. So we will get back to the concept of how do you do translation from that level into the physical address space. So I should call this really physical address space and physical addressability here. Addressability is the minimum size of data in memory that can be addressed physically. Again, this could be different from what your ISA specifies, right? Your ISA can specify the minimum unit you can address is actually a word, let's say, 32 bits. But your memory system may be implemented at the bit level, right? You just have a chip that supplies a bit. And you put 32 of those together and get conform to the specification of the ISA, right? So keep this in mind. And please remind me to change this to physical address space and physical addressability. So you could have different options. And we will see. And these actually depend on the abstraction level of the implementation. Remember, I showed you this picture here. This addressability is really a function of the abstraction level. If you look inside over here, maybe your addressability is actually smaller. Right? And we may see some of this. Okay, alignment is another issue that we will probably cover in the next lecture. Does the hardware support unaligned access transparently to software? Does the hardware ensure that ISA's alignment, if the ISA allows unaligned accesses, how can the hardware support that? We'll get back to this. But let's cover interleaving in a little bit more detail. We've seen this, but why do you want interleaving? You really want this because a single monolithic array takes long to access, and it doesn't enable multiple access in parallel. There are two issues with a single monolithic array. Right? So interleaving solves both issues. The goal of it is to reduce the latency of the memory array access and enable multiple access in parallel. And the idea is, as I showed you, divide the array into multiple banks that can be accessed independently. You can access these independently in the same cycle or in consecutive cycles. You can start the accesses. Each bank is smaller than the entire memory storage, which reduces the latency of the array access, and access to the different banks can be overlapped. The issue is, how do you map data to different banks? Right? Or how do you interleave data across these banks? So this is where you can see the chip-enabled signal better, probably. Let's take a look at the simple interleaved system. Assume that each bank supplies a word, and you have 1,000 rows, and assume that a row is 32 bits, and a word is 32 bits. This is a simple implementation of the interleaving, right? You have two banks, and you have chip enable, let's call it bank enable here, bank enable for each bank. Well, these should be one, right? Looks like I have a bug in my little drawing here. This should be chip enable 1, write enable 1. And there's some logic that determines which chip enable, which bank should be enabled. Right? Actually, let me draw this so that we have the nicer picture. I thought this would be the nicer picture. So this is the case of two banks sharing a single data bus, if you will. Bank 1, you have bank enable 0, and then write enable 0, and then bank enable 1, and then write enable 1. And then you have data that comes out. Right. And when the data is ready, it's gated into this bus, right? So there needs to be some logic that determines who gates the data, right? Onto the bus, onto the shared bus. So this is how you can get a 32-bit data out of two different banks. Erase this. So you need to have a controller that controls this, right? When the controller gets an address, essentially it determines the chip enable and bank enable signals at that point, and essentially enables, bank enable and write enable signals, and then schedules requests to these banks, essentially. So if you get an address that goes to bank 0, the controller needs to enable this bank, right? Yes?
If you have a write enable and you have a gate for each of those,
Yeah.
why do you need the bank enable? It seems like you could tell it that you want to write for each one of those banks, and then you can tell it that you want to read from each of those banks. So why do you need the extra bank enables?
Yeah, you could. I mean, you could optimize the design. That's absolutely true. This is just to give you the abstraction, to hold the abstraction. You could optimize the design, though. You're absolutely right. Yes.
So bank enable just means read, or does it mean read or write?
Bank enable in this case, it means read or write, basically.
Okay.
You enable the chip. So what you can do is without this, you could turn off parts of the chip, right? The bank enable, that's one reason you might need the bank enable. Okay. Let's take a look at the question of interleaving. So how do you interleave the words across the different banks? So what are your options? I think I have some options for you here. Since you have 1K rows, your address is really 13 bits, right? Where do different words go? Well, I guess the bottom 4 bits of your 2 bits of your address are actually bytes in words. So they're lost in your bus because your addressability is really 32 bits for this 2-bank memory. One option is to have your bank bits come from here, right? Which means that your consecutive words, like word at address 0 goes to bank 0, word at address 1 goes here, address 2 goes here, address 3 goes here, address 4, 5, ... Right? This is called word interleaving. You interleave the consecutive words in memory in consecutive banks. So why could this be useful? Well, this could be useful if you're accessing consecutive words in parallel, right, at the same time. Or one other potential option is, I think I put the bank bit here, right? So what do you do in this case? In this case, your interleaving looks like you have the first 1,024 words in bank 0, 0, 1, 2, 3, 4, 1,023, and the remaining 1,022 words in bank 1. Right? So when would this make sense? This could make sense for some access patterns, right? Like what if you're adding the, let's say you have 2 arrays that happen to map to these 2 banks, and you're adding, one array starts at address 0, and the other array starts at address 1024. And let's say this is array A and array B, and what you're doing is A equals A plus B. AI equals AI plus B. I. That way now you can actually access the 2 words that you need to add in parallel at the same time. Right? Make sense? So your mapping scheme, interleaving scheme, heavily interacts with your access pattern in terms of the performance that you see in the end. So you could think of choosing the bank bit from somewhere else as well, right? In the middle, for example. Yes?
Just have a single bus here, so you cannot access them in parallel?
Well, in consecutive cycles. Let me rephrase it. Yes. So the banks are accessed in parallel, right? But the accesses start in consecutive cycles. So if your bank access latency is let's say 16 cycles, you start the first access in cycle 0 at bank 0. You start the next access in bank 1, assuming the next access goes to bank 1, in cycle 1. So you overlap 15 cycles of the bank access. And at steady state, you overlap all of the cycles, actually, if you keep generating requests. Right? But this is not the only way to design, actually. I will get back to that. But let's cover this other interleaving here. Interleaving scheme 3. Let's say you pick your bank bit as, what is this? Let me change this. So you have 2 bits for byte and word. And you don't use this bit for the bank bit, but you use this next bit. This is your bank. So in this case, where do words get mapped? Consecutive words get mapped in the bank, in the different banks. Word 0 goes here, word 1 goes here, right? And word 2 goes here, and 3 goes here. 4, 5, 6, 7. These are the addresses of the words. And maybe you can come up with an access pattern that actually can exploit this. Okay? So that's the idea of interleaving. Multiple banks, and where do you map the data? So going back to your point, it's really not fundamental that with banking, it's really not fundamental that you share a single data bus. This is also an interleaved design. You have bank 0, you have bank 1, and you have 2 different data buses, 32 bits, and they don't share a data bus, or they don't share an address bus. The difference is that this is more costly, right? Yeah, really 64-bit bus here instead of a 32-bit bus. But the same issues apply here. Where do you map the data? Right. Okay? Okay, some questions. Let's see. Okay, we're doing. So this is the same design that we saw in Cray, but not to this detail, right? Cray had 16 of these banks. And it had an 11-cycle bank latency. That's why it had the 16 of these banks, because they wanted to have 11 accesses in parallel, so that they could get 1 word every cycle. And what they did was they had consecutive words in memory mapped to consecutive banks. So they used word interleaving. Because if you're doing an array access, well, vector access, and your stride is 1, then you're accessing consecutive words at the same time, right? Or you need consecutive words at the same time. And they could start 1 access and finish 1 access per cycle. Okay, we already covered this. Can banks be operated fully in parallel? Yes, if you have a design like this. What is the cost of it? Well, we've seen this earlier today with the interleaving for the cache, right? This is more costly. And also, I haven't shown you the conflict mechanism and the routing mechanism here. Here you don't have that routing mechanism, right? In a sense, it's kind of internal. So this is what DRAM kind of looks like, which we will cover in more detail, because cost and pins are a big issue at that level. Whereas this is what L1 caches look like. In L1 caches, you have banks that are kind of fully independent of each other, except for the peripheral logic that determines whether the access actually conflict. Whereas in DRAM, you have banks that actually share the data bus, the address bus, as well as the command bus, which we will see. Okay. So in a sense, even this is an abstraction, just to set you up for the DRAM lecture. Yes?
So if that was a cache, would they have independent tag stores for each bank? Or?
That's right. Yes, because you would like to access the tag stores in parallel also, right? You'd like to have multiple lookups for the tag. So think of this bank as something like this. Tag 0 and data 0. And tag 1 and data 1. Okay? Okay. In a sense, even this is an abstraction. I kind of told you this before. These 32 bits, 32-bit may be expensive also, right? So you may want to be able to supply 32 bits at the same time, But you may not want to design a chip that supplies 32 bits at the same time. And that's what, because pins are expensive when you design these chips. And you want to design, you want to optimize for cost. So the 32 bits can actually come from multiple chips, if you will, each of which can supply 32 divided by n bits. So think of this as n chips supplying 32 divided by n bits at the same time. So that's the concept of a rank, if you will. Basically, that's this picture that I've shown here. You can think of it as this. You have 4 of these chips, each of which supplies 8 bits at a time. This is called a rank. It's a set of chips that respond to the same command and the same address at the same time with different pieces of the requested data. Does that make sense? It's like a rank of soldiers. You give a command to the rank of soldiers and they do the same thing, right? This is each of these chips, you give a command to the chips and they're all doing the same thing, except they're supplying different pieces of the data. Yes?
They each output 8 pins, so why is this better than like one outputting like 32?
Because this chip is less expensive now, right? Because it has only 8 pins instead of one chip, building a single chip that has 32 pins. That's why I call this an abstraction. You put together 4 less costly chips to output 8 bits. In fact, very old DRAMs had a single bit output. Now, many DRAM chips are like usually output 4, 8, or 16 bits. And what system designers do, what DRAM module designers do, is take a bunch of these chips, form a rank, and ensure that you get a 64-bit interface. In this case, you get a 32-bit interface. Okay? So why, again, producing an 8-bit pin chip is cheaper than producing a 32-bit pin chip? And the idea is basically produce a less costly chip and put them together. Okay, let's see if we have enough time. We do have some time. Maybe we'll cover this. Any questions on this, by the way? We'll get back to how this fits in the entire system. Yes.
Why is it more than n times cheaper? Like, if you had...
Oh, is it more than, what did you say?
Because you have n chips now, right?
Uh-huh.
So if you just reduce the cost by a factor of n by having n times fewer chips, then it would still be the same cost. So, like, why is it more than n times cheaper to make?
I didn't say it's more than n times cheaper. This chip itself is cheaper, right?
But, like, why do you care about the cost of a particular chip? Don't you care about the cost of the sum of the cost of your chips?
You do. That's right. But then from the DRAM manufacturer's perspective, they do care about the cost of the chip also, right?
Okay, so just that they get
Yeah.
to make the decision, not you.
That's part of it, but this is also, well, this could be less costly in the entire system. We can think about this during office hours if you want to come. That's an interesting topic. There's a lot more involved in the cost equation here. Any other questions? So you know how to interleave data in the system and what ranks are. So if you look at the DRAM subsystem, it actually consists of a hierarchy like this, if you will. You start with a row and column and 2-dimensional array. You form a bank. And a chip consists of multiple banks. And you put multiple chips together to form a rank to get a wide interface. And you can have multiple ranks in a module. And you can have multiple modules of different channels. Right? That's how you form the system. And we've already seen the Drm Banks structure. I'll describe this to you, and then we can part after that. So this is one concrete example of a DRAM bank, if you will. It's a 2 to the 24 byte array, 2 to the 14 rows, 2 to the 8, 2 to the 10 columns. Each column has 8 bits. So the interface to this bank is 8 bits, if you will. Whenever you do an access, do a column access, you get 8 bits out. And I told you that you latch the row address and the column address separately instead of sending the entire address, if you will, entire 24-bit address, so that you can say pins. Right. So this address comes from the DRAM controller. The row address gets latched, and you activate the row, if you will, and the data gets stored in this row buffer or sense amplifiers. Basically, you amplify the entire row because the charge is very low here. You need to figure out this logic here, figures out whether it's a 1 or 0 and amplifies the charge. And this logic is some sensing logic plus essentially what SRAM is built of. These are cross-coupled inverters that store the data from the entire row. And remember that the row read was destructive, right? Because we discharged the capacitor when we read the entire row. We discharged all the, how many capacitors here? Through the 10 by 8 capacitors. Okay? And once the row is in the row buffer, and the controller knows that a row is in the row buffer because there's a specified timing by the DRAM chip. The DRAM manufacturer says an activate takes some number of nanoseconds, let's say 12.5 nanoseconds. And the controller can be designed to know that after 12.5 nanoseconds, well, 12.5 nanoseconds after sending this row address to the DRAM chip with the activate command, I can be sure that the row that I'm looking for is in the row buffer. Now I can send the column address. Right. And the DRAM controller can send the column address, a 10-bit address, and send a command saying read from this column address. And what the DRAM chip does is essentially muxes out the 8 bits associated with that column address and sends it back to the controller through the data bus. So this is one single bank. A DRAM chip actually consists of 8 of these, similar to this, put together, but they share this address bus, this data bus, as well as a command bus. So you can send an address, data, get data, or send a command to only one bank in a given cycle. Okay? Okay. I think we can stop here, unless you have any questions, and we'll continue with the memory subsystem in the next lecture. Any questions?